All right, so for molecular formulas, we've been doing empirical formulas being the lowest whole number ratio between the atoms. Well, I've mentioned this several times now throughout the way, but for ionic substances, the empirical and the molecular formula are the same. When we write the formula, for example, of magnesium oxide, so we put Mg plus 2, O minus 2. Now that's ionic, has a metal and a nonmetal. And what we learned is, since the charges are already balanced, the correct formula is MgO. The lowest ratio between the atoms is 1 to 1. Now, if you messed up, and remember you crossed the charges and you did Mg2S2, well, we would have reduced it and you would have ended up with MgO in the end anyway. All right, so that's for ionic. So for ionic substances, the empirical and the molecular are always the same. The ratio is always in its lowest reduced form, and the empirical and the molecular are always the same. But for covalently bonded substances, for molecules, not always the lowest whole number ratio. For example, we know C6H12O6. You've learned that in your biology life, your chemistry life perhaps. I've mentioned it several times throughout the year now. And notice that that is not an empirical formula. It's not an empirical formula because you could divide each of these by 6 and get CH2O and end up with a reduced form. Well, that's the difference. A molecular formula gives you the actual ratio, not the reduced ratio. So this one I have circled right here, this would be a molecular formula, not reduced. And then the reduced form of that, the empirical formula, that would be divided by 6, and 1 to 2 to 1 ratio, compared to the actual ratio, which is a 6 to 12 to 6 ratio. So when you do these molecular formula problems, you need an additional piece of information, which I'll get to in a second. Again, vocabulary. Molecular formula, the actual ratio, 6 to 12 to 6. Empirical formula, the reduced ratio, 1 to 2 to 1. Good for that. I wanted to say one more thing, but I can't remember what it is, so I'll move on. Next page, let's go. What's going on here? There we go. All right, so for molecular formulas, the molecular formula is a multiple of the empirical. For example, benzene. Benzene is another organic substance. Notice molecules, nonmetals bonded together covalently. We have a 6 to 6 mole ratio for benzene. A 6 to 6 mole ratio for benzene. Benzene is in a ring like this with carbons, and then each carbon has a hydrogen. And then there's an alternating double and single bond. So you need to know that? Absolutely not. But you know that it is not an empirical formula because you can reduce it. So benzene's empirical formula is CH. Its molecular formula is C6H6. So again, the reduced compared to the actual. I just remember what I was going to say. That would be, if we were to find the percentage of carbon and the percentage of hydrogen in CH. And if we were to do the same thing for C6H6, the percent carbon and the percent hydrogen, they're going to be the same. And so when we solve percentages, we're always going to end up with the empirical formula, or the lowest reduced ratio. So again, we need that additional piece of information to figure out what's the actual ratio. One more of these before we do that, and that is ethane. Ethane is another carbon to hydrogen bond, and it is C2H6. So the reduced form of that would be CH3. So that's called the empirical compared to the molecular. All right, so here's an example. A compound contains 31.10 grams of carbon, 7.872 grams of hydrogen. First, find the empirical formula. Then find the molecular formula, and there's that additional piece of information we need, which we'll get to in a second. All right, so let me solve this. So we have 31.10 grams of carbon, 7.872 grams of hydrogen. If they were percentages, we would have to assume 100 grams, but they're not. They're already grams, so we don't have to assume 100 grams. We're going to divide by the molar mass of each of these. So you can, let me get my calculator out. I don't have to use the one on the screen. 31.10 divided by 12, and we got 2.592. So if you don't know how to do that, go back and watch the one on empirical formulas. 7.794. Okay, so there's the mole ratio. I'm going to divide by the smaller one, and I get a 1. And I get a 3. So this is a 1 to 3 mole ratio. So the reduced ratio is 1 to 3. CH3 would be the empirical formula. All right, so now here's the next part of this. So the next part of this is I want to find out what multiple do I have of the empirical to get to molecular. And so that additional piece of information says that the mass of the molecular formula is 90.18. So 90.18 is what this thing is going to weigh in the end. Now, an empirical formula is the reduced form. So if I multiplied these times 1, CH3 could be a molecular formula, or times 2, or times 3, times 4, etc. You see what I'm doing there? I'm multiplying, I'm doubling the subscripts. So times 2 would give me a 2 and a 6, or times 3 gives me a 3, and 3 times 3 is 9. 4 and 12, etc., etc., etc. And I can just keep randomly doing that until I end up with 90.18. But we don't want to have to do that. And so here's the trick. Find the mass of the empirical formula. So the empirical formula is CH3. That's 1 carbon, 3 hydrogens. 12 plus 3, 0.03 gives me 15.03. So that's the mass of CH3. So then I'm going to say 15.03, the mass of the empirical, times X equals 90.18, the mass of the molecular. So this will tell me how many times am I going to multiply the empirical formula until it equals 90.18. So solve for X. X equals, divide both sides by 15.03. There's the algebra. So 90.18 divided by 15.03, and I get 6. So that means the molecular mass, 90.18, is 6 times the empirical formula. So I'm going to take CH3 and multiply each of the subscripts times 6, and that's the molecular formula. So again, the molecular formula is a multiple of the empirical, and we need that additional piece of information, that molar mass, in order to solve it. Sometimes in the problem, you'll be given the empirical formula. This says the empirical formula is CHOCl, 1 to 1 to 1 to 1 ratio between carbon, hydrogen, oxygen, and chlorine. So find the mass of that. 1 carbon, 1 hydrogen, 1 oxygen, and 1 chlorine. Add them up, 11, 12, 13, 14. So 64.51. So I want to know 64.51 times X equals 129. Now, a lot of times in these problems, they will mess with you by not giving you an exact mass. It'll say it is about 129 grams per mole. So that when you solve this, it may not come out to be perfectly a whole number. So once again, like this guy, we have to evaluate our answer, understand that the molecular is a multiple of the empirical. So this has to come out to be a whole number. If it doesn't come out to be a whole number, we're going to round it to a whole number, but it's going to come out really close. And you can see when we solve this one, it comes out to be a 2. So the correct empirical is CH3OCl. The correct molecular would be C2H2O2 and Cl2. All right, one more. What about if we have percentages? Well, same deal. Vitamin C, ascorbic acid, citrus fruits. We have percentages, so we're going to assume 100 grams. Again, go watch the empirical formula video if you don't know how to do that. 40.9 grams of carbon, 4.58 grams of hydrogen, 54.5 grams of oxygen. Divide by the molar mass. That's going to give us moles. I might as well show you on the calculator this time. So we have 40.9 divided by 12. So I'm going to keep, extra significant digits, 3.408 moles. 4.58 divided by 1.01, I get 4.535 moles. And then I have, how many? 54. 54.5 grams of oxygen divided by the mass of oxygen, 3.406 moles. So from here I got to divide by the smallest one, which is this one. I get a 1. I get a 1. 4.535 divided by 3.406. And you can see this is the other step, if you go watch the empirical formula, where I have to think it has to be a whole number at this point, or one of those decimal equivalents we've been discussing. a quarter, a third, a half, 2/3, 3/4, and this one's 0.33, so I'm going to multiply by 3. If I multiply that by 3, I have to multiply them all by 3, and I get a 3, a 4, and a 3. So the correct empirical formula is C3H4O3. Good, empirical. Now, the molecular then is a multiple of that, and so I'm given the additional piece of information. 176 is what this is going to equal. So find the mass of the empirical. I have 3 carbons, 4 hydrogens, 3 oxygens, 36, 4, 48. Add them up, and I get 88. So the molar mass of the empirical is 88, so I'm going to say 88 times what number equals 176, the mass given to me as the molar mass of the molecular. X is going to be equal to 2, so my correct is C6H8O6. And there we have it. That is a molecular formula from an empirical formula. Again, the thing to remember is, at this point, once again, I have to evaluate. I have to say, this has to be a multiple, so this has to be a whole number. If it's not, then I messed up somewhere. And so I can sort of backtrack and find my mistake. Normally, it is right here in the molar mass, or right here when we find the molar mass of the empirical. So that would be the 2 places to start if you mess up.